Welcome to the GaN Talk podcast, brought to you by EPC and hosted by Maurizio Di Paolo Emilio, Marcom Director at EPC. This show brings to life the stories behind GaN technologies and products. In each episode, you'll hear engineers, executives, and academics share insights on the challenges and opportunities shaping the GaN market. Here is your host, Maurizio Di Paolo Emilio.
Hello everyone and welcome to GaN Talk podcast. In this new episode, today we will talk about advancing systems performance with GaN power electronics. So in today's episode, we explore how advanced power electronics systems are reshaping the performance and efficiency of modern UAV platforms, but also others. So the JetFleet G18 represents a new generation of drones and e-bike designed for high power density, improved efficiency, and optimized propulsion systems. So areas where, as you know, wide bandgap technologies such as gallium nitride are playing a transformative role. So to better understand the engineering behind this platform, JetFleet G18, our guest is Jernej Fajdiga, electronics engineering graduate student and hardware innovator. Hi Jernej, welcome aboard. How are you?
I'm excellent.
So our guest will walk us through the architecture of this platform, his project, and discuss how GaN technology, particularly solutions from EPC, helps enable higher switching frequency, improve efficiency, as I mentioned, and would offer more compact power electronics for demanding UAV applications. So in this conversation, we will dive into the design challenges of drone power systems, the integration of GaN devices into motor control and power stages, and the broader impact of wide bandgap semiconductors on the future of autonomous aerial platforms. So Jernej, where are you located?
Right now I'm in Maribor in Slovenia.
Nice place. So to start, Jernej, please introduce yourself and give us a bit of your background.
My name is Jernej Fajdiga. I'm finishing my master degree in electronic engineering in Maribor. I'm also the founder of JetFleet. I got into the hardware very early when I built my custom 3D printer from scratch in high school. That gave me the passion for engineering. My next project was e-bike and e-scooters. This led me to design my own motor inverters. This was a long process. I have many failed prototypes and many burned FETs, but it was worth it. I have the first customer found me on Discord when I helped them debugging their inverter designs. They liked my work. They hired me to build a custom inverter for them. That later pushed me to start the JetFleet. Once I had a working silicon MOSFET inverter, I wanted to push it further. I moved to GaN. That became the JetFleet G18 inverter. It is 200 volt, 300 amp peak inverter. Right now we have a first beta tester using it for a few weeks. He already did a few hundred kilometers on it with a one wheel. He's using 168 fully charged battery and motor currents peaking above 200 amps. We have a new batch of 20 pre-production units in production, and we will send them to more beta testers. So far, it works better than expected. This GaN inverter, JetFleet G18, is also a core of my master thesis, where I will measure its characteristics and compare it to silicon inverters we have.
Thank you. So the JetFleet represent a nice example of how modern UAV platforms are evolving towards higher power density and more integrated electronics. So can you start by walking us through the overall architecture of the JetFleet G18, in particular the power electronics and propulsion system, and explain what design challenges you faced at that time?
G18 is a three-phase motor inverter. It's using 18 EPC 2304 GaN FETs. I have designed several MOSFET-based inverters in last years, and this give me a max experience to make a working GaN inverter in a first try. The biggest challenge with silicon design I have was the power loop parasitics inductance. If the coupling caps and the FET layout is not tight, we get a large power loop. In this creates voltage spikes during the switching. And the second problem was a current sensing noise. The fast switching transient couples into the analog sensing trace. When we solved those problems, we didn't repeat them on the GaN layout. But with the GaN, it brought us two new challenges. The first one was thermal management. The GaN FETs are very small. Heat concentrates in a tiny area. So we are forced to use high thermal conductivity putty rated for 14 watts per meter Kelvin and a custom heatsink that maintains the steady gap of 0.3 millimeters. And the second challenge was paralleling the FETs. We have 3 FETs in parallel per switch, and every single one must carry equal currents and see the equal inductance. Layout must be perfectly symmetrical, otherwise we get unbalanced current sharing. This will create the thermal hotspots, and this can lead to the failure. So,
companies like EPC, as you mentioned, did several advancements in terms of GaN, enhancement mode GaN devices in particular, that enable extremely compact power stage and the motor drive. This device support higher switching frequency, reduced losses, all parameters that are critical in space-constrained systems like drones. So, our EPC's GaN devices that you mentioned integrated into the platform, G18 power electronics, in particular in the motor drives, DC-DC stages, what specific, in particular, reference design probably influence your architecture?
The goal was to make a 168 volts inverter, so we must use the EPC FETs because the silicon cannot match this characteristic. We didn't use the EPC reference board designs, as we know we can do it better. We have an experience from the previous failed attempts. But the EPC technical documentation was very valuable. The biggest insight was in the inductance shared between the power loop and the gate drive loop. This degrades the switching performance. So the paper was very helpful.
One of the key advantages of GaN in drone propulsion systems is the ability to operate at a significantly higher switching frequency than silicon, so which allows smaller magnetics, capacitors, improved efficiency, of course, and so on. So how does the higher switching frequencies enabled by GaN impact the design of your platform in terms of motor control, inverse stage? What benefits does it bring in terms of propulsion efficiency and flight performance in particular?
The higher switching frequency change both sides, the hardware and the motor side. On the hardware side, in the inverter, the higher frequency can fully eliminate electrolytic capacitors. This is not just the size reduction. Electrolytic are usually the first components to degrade over the time. On the motor side, with silicon, we have higher dead time. This creates the distortion and makes motor louder. With the GaN, dead time is close to 0 and motor is silent. It also enables higher frequency and reduce the current ripple in the windings. Less ripple also means less heat in the motor. For UAV, what matters the most is the mass and the efficiency. GaN makes smaller, lighter, and more efficient inverter with cleaner output. This directly translates to longer flight time.
So one topic is thermal. So increasing power density in UAV will raise challenges in terms of thermal management. So which are your considerations and challenges in this regard?
Yeah, for thermal, we have multiple FETs in the parallel, and they need to be cooled equally. If one FET have higher temperature, it will also have the higher RDS on, so it will dissipate even more heat, and it can fail. It needs to be cooled evenly.
So, GaN is rapidly expanding beyond power supplies into motor drives, LiDAR, power systems, integrated power stages for robotics, UAV, enabling, as you mentioned, smaller, lighter electronic architecture. So looking forward, how do you see GaN evolving in this platform like G18 you mentioned, in particular in terms of propulsion electronics, next generation autonomous systems?
Yeah, GaN is pushing toward deeper integration inverter inside of the motor. This is already happening. It's not just idea. We have some customers already mounting silicon-based inverters like JetFleet F6 directly inside of the motor in one wheel. As GaN inverters become smaller and more power dense, this kind of integration become easier. This will lead manufacturers to integrate inverters into the motor, as this reduces system complexity and it decreases the system weight.
Thank you. So, to conclude, which are your expectations in terms of job professional, and if you can tell us more about your final thesis and what's next from you?
My final thesis is focused on the GaN inverter, this G18, but it also at the same time we will compare it to the silicon inverter we have. It's still in the testing and measurement stage. Right now we are facing problems with measurement equipment. GaN requires fast oscilloscope and probes. In the future, it's definitely the inverter integrated inside the motor. This is what will come next. For me, on the short term, I will build an inverter for the linear motors and probably a GaN charger. On the long run, I will keep designing state-of-the-art products.
Thank you, Jernej. Thanks a lot for coming on GaN Talk podcast. Thanks for joining us, and see you soon. Thank you.
Bye.